Hi everyone. So let's start dissecting the theory of congruences. So the first theorem it tells us that the congruences, as we defined it, behaves similar to equality. So we have the following theorem: 2.1. Let n be a positive integer for all a, b, and c inside of z. We have that 1a is congruent to a mod n. The second thing is that if a is congruent to b mod n, then b is congruent to a mod n. And 3 is if a is congruent to b mod n and b is congruent to c mod n, then a is congruent to c mod n. So let's prove this. So first of all, we have that a minus a is 0, and any number divides 0. So in particular, n divides a minus a, which is 0. N divides 0, which is a minus a. So therefore, a is congruent to a mod n. The second part is if a is congruent to b mod n, then there exists a k inside of the integers such that we can reach a minus b through n, as n divides a minus b by definition of congruence. So then if we multiply k by -1, we are multiplying the whole thing by -1. So n multiplied by -k, that would be b minus a for minus k belong to z. So therefore, n divides b minus a, which means that b is congruent to a mod n. The third thing is if a is congruent to b mod n and b is congruent to c mod n, then there exists a k and a q belongs to z such that a minus b is n times k and b minus c is n times q, which means that if you add the a minus b together with the b minus c, that is equal to n multiplied by k plus q. But this is, the b's cancel as it's alternating, so that a minus c is a multiple of n for k plus q belonging to z. And we are done. That proves the first theorem of this subsection. So the first two theorem that we'll prove essentially tells you that you can transport all algebraic data that you have on Z on congruence classes, and that's what we will see in the next subsection. So we have the following. So remember, with equality, we have the following identity. So with equality, we have the following identity. We have if A is equal to B and C is equal to D, then A plus C is equal to B plus D, and AC is equal to B and D. So it turns out that this also is transported to also congruences as well. So this is what we expect anyways, because like if we analyze it in terms of equality, we defined the, as we'll see, like that part is really captured in the lemmas and the theorems, etc. Like as you'll see that like since equality satisfies that, and then like congruences just capture remainders, same remainders, so then we expect the like the addition as well as multiplication of integers to get transported under congruences as well. So this is the main idea. So let's prove the following result. So theorem 2.2. So this tells you that if A is congruent to B mod n, and C is congruent to D mod n, then A plus C is congruent to B plus D mod n. And the second part, we have that AC is congruent to BD mod n. So yeah, so let's prove this result. So first of all, you have that A. So what do we want to prove anyway? So we want to prove that n, so for the first one, that n divides A plus C minus B plus D. Or, in other words, we want to prove that n divides A minus B plus C minus D. So everything is defined in terms of equality, so we expect that the technical parts of math will get transported to prove it anyways. So that's the main idea. So here, let's continue the same color. So since we have that A is congruent to B mod n and C is congruent to D mod n, so that means there exists a p as well as a k belonging to the integers, such that you have that a minus b is n times k and c minus d is n times p. So then if you add them together, you get a minus b plus c minus d. This is n multiplied by k plus p for k plus p belonging to the integer, and therefore we get what we want. So therefore we get that a plus c is congruent to b plus d mod n. Alright, so that's good. So let's see the second part. So the second part tells you that AC is congruent to BD. So we want to show that AC minus or n divides AC minus BD, which is the same thing as AC minus BC plus BC minus BD. We just added a 1. Added a clever 0. That's it. So not a 1. So this is the same thing as A minus B times C plus B times C minus D. And like the reason that we have to add this clever 0 is just when we expand multiplication, things cancel out. And so there is a hidden telescope variable, so to speak. Just as we have seen from problem 1. This hidden telescope variable appears in the addition part. So yeah, so anyways, so we have the following. So since A minus B is nk, and C minus D is n times p. So that means we can replace A minus B. We can replace it by nk, and we can replace C minus B by np. So we have nk multiplied by C plus B times np. So here let's factor out an n. Okay, C plus BP. So indeed you can see that, so indeed you have that N divides AC minus BD, and we are done. So yeah, I'll start covering congruence classes next time, as I like to keep the videos short, so then the ideas are captured by people rather than getting it distorted. So I'll see you guys in the next one, and yeah, hope you enjoyed this video. Bye.